magnetic fields and stuff like that, then it can be a longer scale.
Because you can recover it even from part of that. So.
Yeah, so you know, of course, it's actually not that clear that you can measure beta that well. If you consider the density matrix, or if you consider two Gibbs states with a temperature that differs only by 10%, they're actually not that distinguishable, right? Because they're both diagonal in the same basis, and you know, one of them will look like that, and the other one will look something like that. But if you have many copies, this turns out not to be a problem. I'm really running out of room here. And the reason is just that if you're trying to distinguish between state A, many copies of it, and state B, many copies of it, right? The inner product is just AB to the n. And if we call that 1 minus epsilon, where you know A and B might be very hard to distinguish, this will still go like e to the minus epsilon n. And so with several copies, you can distinguish with high reliability. Does that make sense? Okay. So maybe that's not, maybe if you think, okay, whatever, there's a bunch of copies of this information out there, maybe that doesn't surprise you very much. You say, fine, that happens. But as Peter mentioned, this can't be true for most of the information in the universe. So we've noticed that a lot of these things we care about, macroscopic degrees of freedom, and these hydrodynamic variables, which of course are applied all over the place, do seem to be redundantly copied. And this can only be true for a rather small subset of all the degrees of freedom. And so what I'm going to try to show to you guys is that already this constraint gets us very close to finding a preferred branch structure, or at least it gets us to a structure that, that those branches will be a coarse graining of. Okay?
So when I heard that last couple sentences, I was thinking, isn't it really a constraint on that there isn't so much information in the universe as opposed to...
Well, it depends what you mean by information in the universe. I mean,
so that's what I'm hoping. I mean, I'm thinking, so if the limit is on, if the limit is coming from saturating the space to hold the information, that's the low entropy of the universe we're talking about.
yeah.
And it is low, so you can. So we're not about to saturate it.
I see.
And so, now I'm trying to suss out what exactly you mean by you can't do it for all the information in the universe. So that's sounding a little bit like maybe you can, but.
Right. So what I really mean is that there are these many copies. So if we just had a bunch of qubits, they were all unentangled with each other, they would all kind of store their own bit of information.
Right.
But
every qubit had to be part of a long line of correlated ones.
That's right. Then.
But that's just saying most states are not like that.
Absolutely.
So that's low entropy, but the universe is low entropy. So how do I know?
Well, he's saying that when something equilibrates, like this box of gas, most of the degrees of freedom can't be. Only a few of them can be redundant like that.
So that's an interesting topic, and I agree and provoked in my talk on Monday that we don't quite know how to fully address that. But the universe is not in equilibrium by any measure, and so maybe this is all. So maybe we're not. So my guess is we're not nearly saturating this in the actual universe.
I think we're not nearly saturating.
He's not saying we're saturating yet.
Yeah. No. Certainly not.
Someday.
No. Actually, what happens in the far future for information theoretic reasons, I don't have actually a strong opinion on. What I mean is that of all the qubits in the universe, that's some number, and then the number of bits that are redundantly stored on those qubits in the universe is substantially less.
just because you need the multiplicity? So
Just because you need the multiplicity.
So it's just, got it.
Yep, that's it. And like, and just to be clear, so
It's not about saturating, okay, I see, I think I get it.
so it is both, right? So the number of photons that are bouncing off macroscopic objects.
If you're using up bits to duplicate records, they can't have their own information.
That's right.
That would be
And-
classical.
Yeah.
Right.
No, it wouldn't be classical enough.
Well, it sounds like you're not using up so many bits because there's zillions of positions of like the molecules or whatever the dots represent in your
Yes.
there. And you're saying, well, they're redundantly storing just like pressure or temperature or something.
That's right.
But they also have their own individual positions of momentum and stuff, which they also know about.
Well, so they don't. Right. So if they have thermalized, the small volumes have thermalized, then it is a property of thermal states that they don't have correlated informations on length scales longer than their interaction length, right?
Yeah.
So, right. So when you're, Charlie's example that I love is that when you're in an oven, like you can't see anything. Like the stuff that's in front of your eyes tells you nothing about what's going on the other side of the oven.
This is assuming that you are still alive. Well, it's true if you could see the black body radiation.
Yeah, if you got yourself in a little spaceship, or it was a really big oven or something, and you were protected from the heat, then just looking locally would tell you nothing, right? You can't see the features on the inside of an oven. Okay. So the thing is that all these classical degrees of freedom are very recorded, and that thermal states don't have this sort of information, and that most states in Hilbert space are not thermal, or rather, most states in Hilbert space are thermal, so most states in Hilbert space don't have this feature. So the state describing our universe is special. Okay, so that was...
Sounds like you've said the opposite of what you were originally setting out to say.
You caught me in a contradiction, John. No, go on.
I don't think I have, but
I'm just...
misunderstanding something. That at some point you said there has to be blank paper to record this information on. There has to be some sort of low entropy part of the universe, at least, to talk about having this information at all. And
Yep.
now you've gone to everything's thermalized, and there's really almost no information.
No, I think, well, we're in a transitionary period, right? So we start at a time near the early universe where there has not been very much branching. There will be not very much information that's recorded because not very much has happened. At the very late universe, we will be all mixed up and there will again be no information redundantly recorded. But in the middle, there is going to be some sort of maximums. And so this very, very simple idea that a sensible notion of complexity should kind of start from zero, reach a maximum, and then come back down during thermalization is, of course, been discussed many times before. Right? So yeah, so let's put this on the lattice because it will allow us to be precise and prove some theorems about it. And it looks like we're going to be able to use them to run simulations of out of equilibrium quantum systems faster. Who knows if it will really help that much, but it does seem to be able to help for at least a little bit. So again, the thing that we're searching for here, and I know that we did these slides before, so I won't drag them out. We're looking for a time-dependent orthogonal decomposition of the wave function. And we want that coherent superpositions, the superposition is indistinguishable from the corresponding incoherent mixture for any kind of a local observable. Of course, for arbitrary observables, we can always distinguish between rho and psi if they are different in a non-trivial way. But for some sort of sensible definition of local, we expect not to be able to. Another thing we expect from this is that branches fine grain under time evolution. This is just a requirement we would have from the internal consistency of the Copenhagen interpretation. That we'll have some spreading here. Well, this is psi at the the initial time, psi 1, psi 2, this is psi 1, 1, psi 1, 2, psi 2, 1, psi 2, 2. And we expect that, so at every level, every horizontal level, these are all orthogonal and they all add up to psi. And there's a ordering on these states. So,
I'm confused about the
yeah, good.
previous slide. I mean, somehow, first you choose what's the definition of local observable, and then that defines where the available branches are.
That's right. So the definition is definitely going to be grounded in a sense of spatial locality. That's like an input into the whole discussion. One way to think about it is that the traditional theory of decoherence is based off of an assumed system environment split that is sort of taken and comes from nowhere. And the idea is to improve on that by deriving the split from something that is more universal, which I'm going to take to be spatial locality. So you always are going to be relying on a tensor product structure somewhere in your state space. If we don't have that, we need something else, because if we don't have that, then we just have a state that's just kind of spinning around unitarily and there would be nothing interesting going on. And it seems like, although of course me and Andy want to go at this different directions, but it seems like, one eye Andy, that this spatial locality seems like as solid a foundation as you could hope for. Was there another question? Yeah.
If the expectation value of all the local observable states are the same, shouldn't this imply that the states are the same?
Not for local observables. So local observables is some subset of all observables, and so you can have two different states that have the same expectation value for local observables.
Isn't there usually the assumption that the algebra of local observables is dense in the set of all the observables?
Yeah, what do I want to say here to make this precise? I keep missing it.
Is based on a set of local observables. So.
Right. Yeah, good. You're right. I should have been more precise. What I mean is some sort of reasonable number of them. So I'm gonna put a. You're not going to be able to have so many local observables. It's going to be about cutting off the endpoint function at some sort of non-huge n.
Okay.
Another question.
Yeah, please.
I'm not understanding the words you're saying. You want to have a system and maybe environment or other systems split.
Yep.
That isn't just assumed.
That's right.
And you're saying, well, are you assuming a tensor product structure, or are you going to derive it?
I'm going to assume a microscopic tensor product structure given by spatial locality.
But isn't that already what I meant by a system and an environment? That it's two spatially isolated things?
They are spatially isolated, but you cannot consider every spatially isolated thing to be a system. So just like we were saying that not all the degrees of freedom can be recorded, so not every gas molecule, even though it's spatially separated from other gas molecules, or every microscopic patch of the quantum field can't be considered its own system, because you could not record everything about everything. Does that make sense?
With anyone I wanted to, I could record everything about that particular one. I could design some experiment and say, I'm going to call this guy the system and pick them out.
That's right. So the question is if you handed me a many-body description of the experiment, so an entire sketch of you and the device, maybe the whole room, whatever. Could I identify what basis the experiment was being done in, or is that just arbitrary? And the claim is that there's going to be a special basis. All I will need to know is the many-body wave function with respect to some preferred microscopic tensor structure, but you will not need to tell me what the device is. And the nice thing about this is that we hope to use the same criteria to derive both that, and also if you just gave me a quantum description of, no, it's gone now, a fluid, I would be able to derive the hydrodynamic variables as preferred variables. Okay. Right, so these are the three sorts of, or three examples of things that we would, or four examples of things that we would want to this criteria to pick out. Okay, so here's the definition, and now we can be very precise about it. And there's only like 2 or 3 slides here with math, and I think it's pretty elementary. And so there's like several indices, but they all have a meaning, and they can all be understood in the next 5 minutes. So I encourage you, if you're going to pay attention at all, to pay attention to this point. So I'm going to define a redundant set of observables at a scale L. So pick some scale L, and we're going to make this really concrete, I'll let you know to what extent this m can vary, but let's pick an m that's greater than 2. So we're going to pick a scale L and an m greater than 2, and we're going to define a redundant set of observables that are local to disjoint regions of that size, right? Sorry, I'm misspeaking here. We're defining a redundant set of observables to be a set of observables that are local to regions of this size and are classically correlated on a state. So this is going to be a statement both about observables and about the state at a given time.